Okay. Good morning, everyone. My name's Ewan Fitzsimons from the UK Astronomy Technology Centre in the UK. I'm the technical lead for the Optical Bench, and I'm going to give you a fairly high-level overview of where the design of the OB is at the moment and some of the recent developments we've made towards it. So the Optical Bench itself, in terms of looking at a standard cartoon of LISA, is this bit here that sits between the GRS, the test mass, and the telescope. And it's where we form all the interferometric combinations and prepare the laser beams. What it actually looks like at the moment is this. So this is the LISA Optical Bench as it is. Those of you who've been out may have noticed that we have a 3D printed model at just under half scale of this sitting on a table outside, which is really quite nice to be able to hold in your hand and see it. So we have the Optical Bench itself is this disk of zero-dur, and we have a dual-sided design, so we are populating components on both sides of this. The A side, which is the one we're looking at the top here, hosts the TX-RX transponder, so it's all the functions required to exchange laser light between the two spacecraft and measure the inter-spacecraft distance and bring in the science signal. And then in the B side, which is the bottom one, which I'll show you later on, is where we have the local interferometry, so the reference interferometer and the test mass measurement. So our way of looking at it is that the B side is like the Pathfinder side, and the A side is all of the new stuff that we have to do in order to be able to bring the long arm measurement into LISA. So, of course, when you look at this, the biggest thing that you see here is this giant yellow thing, and this is the base plate. And without the base plate, we don't really have anything. So this is a single piece of zero-dur, which is an ultra-low expansion glass ceramic. And this is basically our ruler. So if the interferometer is a ruler, we're only as stable as the thing we make the ruler from. So the stability of this thing is absolutely crucial. It's dimensional stability, which is what zero-dur brings us, but also the flex of this thing. If this thing moves about, then our measurement is ruined. So how you mount this thing and keep it nice and stable is critically important. So this is why it's a single monolithic piece, and we cut holes through the side to reduce the mass. And then it's going to be mounted into the spacecraft structure via these flexures on the side. This is a change from where we were a couple of years ago, where we had these insert plugs, which were Pathfinder heritage. But with the loads that are predicted to come from the launcher, these aren't quite going to cut it, so we've changed the designs of these flexures, which we've now actually tested. So just recently, we developed with the IDS engineering team a mechanical prototype of the bench. So this is a 1-to-1 scale aluminium dummy. It's representative in mass and moment of inertia and stiffness as well. And mounted around the side of it, you see there are these 3 titanium flexure blades. So these are the current designs of the ones that we want to attach to the optical bench. And we put this on a shaker table 2 weeks ago, and this should work. Subjected it to 12 G of sinusoidal vibration in multi-axis and also random vibration. And this was primarily a test of, does this thing match our finite element analysis? Does this thing respond the way that we think it does before we take the next step and glue these things onto a piece of zero-dur and put it on a shaker table? And this was very successful. The next thing that's coming is the full engineering model of the base plate. This is currently under manufacture at Thales CESO in France. So this is one of the blanks that CESO have that they're using to make this thing. And this first one that we're going to get here, which will come early next year, we will use to make the full engineering model of the optical bench, which will be the first fully functioning, performing LISA optical bench that we will build. So that's coming over the next 2 years. And we've also done various test parts of this as well. This is a prototype sample that we had CESO make, where they've started to test this lightweighting system. They've also put a hole through from A to B to test the periscope hole, because we need to exchange light between the two sides of the optical bench. And we've also been developing the processes for how to actually glue these things onto the zero-dur. And this is a CT scan of, this is actually an insert rather than the blade, but a CT scan of what the adhesive layer looks like, where you can see quite a lot of air bubbles. So this has been really useful for improving our ability to do these. We have to inject the glue to be able to do it. And this has been a lot of work that's been going on recently. So that's the base plate. If we go back to the optical bench itself, where we start here is with laser input down here. So these are the fiber optic cables that come off the optical bench. And these will connect to the laser, which is being provided by NASA. They terminate here at these parts that we call the fiber injector. So this is the component that has to take the light out of the fiber, the 2-watt light, and turn it into a collimated free space laser beam. And so this has been a big development. We flew these in Pathfinder, but not ones that are capable of handling the 2 watts that we need for laser. So we've changed the design to make them monolithic. So these are constructed purely from silica with a molded lens in the front, and they're built up with hydroxide catalysis bonding with the fiber attached into this part. We then have to characterize them and align this spacer onto the front with micron tolerances in order to achieve the correct collimation of the laser beam, and then we can hydroxide catalysis bond the lens onto the front, and we effectively end up with a full expansion in glass of the laser light. The laser beam then comes out of the fiber injector and passes through this element here. So this is the fiber switch unit. This is effectively 2 rotating half-wave plates, and this is the mechanism that allows us to switch between the main laser and the redundant laser. This is being provided by Czechia, and it will be covered in Ada's general talk on the IDS, which is happening tomorrow at 12. So after the light comes out of the fiber switch unit, we then walk it around the optical bench. So these elements you see here that are the colored ones, these are the mirrors and beam splitters, which are hydroxide catalysis bonded onto the base plate, and I'll talk later on about how we do that. And then the next thing we come to is the TX clip. So this is the clipping aperture that allows us to mode match the laser beam to the telescope. It looks like this. It's diamond-turned aluminium, so that we get a very, very good roughness surface, because we take 160 milliwatts out of the laser beam here, and we have to dump that with very high efficiency, because that's 160 milliwatts of potential stray light. So that's a really difficult problem, actually. And because it's a diamond turned, we also get a really high quality aperture. So we get a 90-degree knife edge aperture with a 1 micron circularity over the 2-millimeter hole. And a prototype of that is currently at NASA Goddard being tested with the engineering demo telescope that they now have, which I guess Ryan will probably talk about on Friday. After the light passes through the TX clip, we have the point-ahead angle mechanism. So this is a 1 degree of freedom mirror, which corrects the point-ahead angle of the laser beam to the far spacecraft to correct for the radial velocity of the spacecraft orthogonal to the laser beam direction. This is coming from the Netherlands for the EM, and then responsibility is switching to Germany for the FM. And again, Ada will talk more about this in her talk tomorrow at 12 o'clock. After the PAM, we then have the TX beam alignment mechanism. This is very similar to the fiber switch unit, but we have 2 inclined optical plates, and they allow us to adjust in flight the alignment of the laser beam. And this is used to compensate tilt-to-length coupling so that we can trim out the on-ground alignment of the system to compensate for all the alignment errors that happened as we build up the system on ground, and also compensate the alignment errors that build up as we go to space. After this, we pass the laser beam into the telescope. So this is where almost all the light is going. As much light as possible is going up off the bench here into the telescope. This works via polarization multiplexing. So we have a polarizing beam splitter and then a wave plate. And on one end of each arm, we have a wave plate, and it allows us to send S-polarized light one way and P-polarized light the other way. And that means that we can bring in from the other side this RX beam. This is our few hundred picowatts of light now coming in the other side, and it is able to transmit through this optic rather than reflect off it. So that's how we multiplex between the 2 beams. The first thing we do with this light is send it into the constellation acquisition sensor. So this is a wide field of view detector that we use to find the far spacecraft in the first instance, because the field of view of the interferometer is about 2 microradians, whereas this will have a field of view more like 200 microradians, so it's significantly larger. This is coming from ESA, and there's a splinter session on constellation where there are a couple of talks on potential designs of this kind of thing on Friday afternoon. Then we take the RX light and we continue to pass it around the optical bench. We have an identical beam alignment mechanism, and then we have an identical clipping aperture. And these are doing exactly the same functions as these ones here. They're just doing it on the received light. Then finally, we walk the received light to the science interferometer. And this is the beam combiner that actually gives us where the science signal will appear. We mix it with a sample of the outgoing TX laser beam, and then we pass it through 2 imaging systems. And we're currently building the first prototype of one of these right now. I hope to have a picture to show, but it's not quite ready, so I can't show it. These are monolithic catalysis-bonded people relay systems, so they should be extremely stable. And they image the RX clip onto the detectors. And they do 3 things. They help remove the tilt-to-length coupling. They match the size of the beam onto the size of the QPD, because the QPD is a little bit smaller than the size of the clip, so we have to compress it slightly. And they also suppress the diffraction rings that would come from this clip, which would be quite severe and would degrade our contrast. So we need this system to do these things. And then finally, we have the 4-quadrant photoreceivers. This is where we're detecting across, splitting onto 4 detectors and detecting the science signal. And Tamesh gave a talk yesterday about these, and Adam will also cover tomorrow in the IDS talk a little bit more about them. Beyond that, we also have a few beam dumps here, so you can see these here. These are here for straight light control, so we have multiple ghost beams across the optical bench that we need to deal with. These are some prototypes that we've just recently built. These are our parallel plate design, so it's very similar to the design of beam dump that they use in LIGO. And they have very, very high efficiency. So we built a system to test these, which is able to measure how much light comes back up the laser beam you send into it to dump. The peak height here is the thing of interest. So we put a commercial beam dump from Thor Labs into this, and it comes up at about minus 60 dB suppression, whereas our beam dump is giving us about minus 110 dB when it's dirty. And that's significant because our modeling told us that this should be limited by how dirty it is. So the scatter of the particulate contamination should be the limit for it. So we cleaned it, and we got it down to minus 130 dB. Which is right at the bottom of where our modeling said it should perform. And we need something like minus 70. So these things are really, really nice, and they should really help control the beams that we need to dump. OK. Then finally, we have this component here on the A side, and this is the periscope that allows us to transfer the beam to the B side. This is what the B side looks like. And we bring the laser beam back out, and then the first thing we do is route to these 2 power monitors. These are part of the laser system, and they're used to stabilize the in-band RIN. And Tony Yu will talk about these later today in his talk on the laser in this hall. We then pass a beam off the B side of the optical bench up towards the test mass. And the power monitors are positioned very close to this beam because we need to stabilize the RIN of the light because the in-band RIN matters for the force noise in the test mass. This is why the power monitors are positioned very close to this pickoff mirror. We use a circular polarization scheme to return the light from the test mass. So we have another set of wave plates, and this lets us bring a light back through this polarizing beam splitter and to this optic here, which is the test blast combiner. We then have a part of the TX beam that goes to the reference interferometer. Sorry, I need a drink of water. That's a lot better. OK. Finally, we send a sample of this red TX beam that we brought down from the other side into the backlink. And the purpose of the backlink is to allow us to exchange some TX light to the beam on the other side of the spacecraft. So we exchange light through this fiber, and that's connected to the exact same thing on the opposite OB. This provides a local oscillator and allows us to achieve phase referencing of the laser light between the 2 sides of the spacecraft. And we recently tested this by passing light from one fiber injector into another one, and we achieved something like 90% input coupling, which is great, is the level we need to be at. We then have another one of these fiber switch units, which is to allow us to do the redundancy on the backlink, and this is identical to the one on the other side. So having sent light this way down the fiber, we're now going to get light back up the other way, and this provides our local oscillator, which is this blue laser beam here. And this completes the interference signal here. We get a beat between this red beam that's bounced off the test mass and this blue one, and this is our test mass interferometer. Again, we have two of these imaging systems, and these are imaging the test mass onto the detector to mode match the beam properly to the diode. And then finally, we have the reference interferometer here, where we have two more imaging systems and another set of 4 QPDs. And here, the imaging systems are really just providing compression to match the size of the beam to the detector. OK. One thing that's particularly nice about this compared to pretty much all the designs of OB that we've had up until now is how efficient it is. So particularly looking at optical bench designs since we had to go double-sided, which was back in 2011, this design has a significantly improved routing of the beam, and this is reflected in the number of optical components that are present. This, the design of OB we have now is comparable to LISA Pathfinder in the number of optical elements that are required to actually achieve it. So I think there are something like 6 elements that are not absolutely mandatory. So we can't really do much better, which is really, really nice, and a significant improvement compared to where we were a few years ago when we had a much more complicated design. OK, another thing we've been working on is an engineering model of the backlink. So I talked about the backlink as being this exchange between the two sides. One feature of this is that you can't test this very easily with a single optical bench, because you need 2 optical benches to properly test the function of this thing. So we're building a dedicated test setup just now to check this. And what you imagine that this looks like is that you put a line down the middle, and one side is the left side of the spacecraft, and the other side is the right side. And then compared to the optical bench, what we have is all of the components that matter in terms of testing this system. So we have 2 input fiber injectors, which replicate the coupling of the light from the laser onto the bench. We then have all of the optics required to link that down and through into the backlink fiber. And then we have 2 reference interferometers. So we've taken the parts of one optical bench that really matter for constructing this backlink, and we've duplicated it and mirrored it so that we get 2. And then the key extra thing we get is this, which we've added a dedicated reference interferometer. And this lets us have an extra witness to be able to test the performance of this thing as we measure between the 2 sides. So this is under construction just now, and it will be tested at Albert Einstein Institute in Hanover in a dedicated test facility. So it currently looks like this as of last week. So a large number of the optical components have now been bonded on. The interferometers are still to go on. And we have 6 fiber injectors sitting, waiting, ready to go onto this. That will be the next thing that goes on. The little picture of the beam dump army I showed earlier on, they have been built to go on this as well. And then we also have a dummy of the fiber switch, because a key thing that this has to demonstrate is that this redundancy concept for the backlink of having 2 backlinks in parallel with a polarization switch between them actually works. This has never been shown before, so we need to demonstrate this. So this is a key task that this has to do. OK. So in terms of building these things up, we've got all these optics that have to be attached onto the optical bench. I showed the plot where it's only 30 or so, but that's still 30, and we have to build of order 10 benches. So we have to put on something like 300 optical components, all using this hydroxide catalysis bonding technique, which, as anyone who's been to an OB talk before will perhaps remember, has this feature whereby it cannot be undone after about 90 to 120 seconds. So it's quite a high pressure, high stress process. So the thing that we've been developing to help us do this over the last few years is this robotically assisted bonding system. So what we have is basically taking as much as possible the human out the loop. So we have a robot arm, and then hanging off the end of the robot arm, we have a hexapod. And the robot arm looks cool, but it's actually just a very fancy system to hold this hexapod in a very stable place. And we use the hexapod to control the alignment of the optic. Under the hexapod, we have our custom metrology system, which we call SuperMint, which just stands for Surface Parallelism Measuring Interferometer. And then under this, this is a demo base plate, which I will tell you about in a moment. But you can imagine that the LISA optical bench would sit here in this position. So a zero-door cylinder, and this thing would rove over the top and place the optics down. So we have an optic hanging in a gripper underneath this thing. And in this case, this silica disc is standing in for the zero-door base plate. We would then have an input beam launcher, which in the real OB would be a fiber injector. And we bring a laser beam off the component and down into here, into our calibrated quadrant photodiode pair. This is our alignment target. This is the magic that lets us actually work out how do you align a laser beam to a test mass that you don't have. This is the answer. This is what we developed for Pathfinder. And it lets us pre-position, using a coordinate measuring machine, this target to micron accuracy, so that we can align a laser beam and know that even though we don't have a test mass there, or even though we don't have a telescope there, we're going to hit it with the required alignment tolerance, which is in the microns range. This, so this is the system that we set up and the system we now tested. Just as a reminder of how this actually works when it looks like, this is the prototype in Glasgow, and I have a couple of views of it, one looking in from the side and one looking down from the front. And what you're seeing is the hexapod is holding the component about 100 microns over the base plate. So there's a 100 micron gap here to where we want it to finally be. And this is the optic that we have here. And this is this fused silica base plate, which is standing in for the zero-dur bench. And we're bringing a laser beam down from this metrology head, this supermint system that's hanging off the bottom of the hexapod. And then we get a return from the bonding surface, and we get a return from the underside of the component. And we can do interferometry there, and that gives us a measure of the absolute distance, not just the relative distance, but it's actually an absolute measurement. And we get a measure of the tip and tilt of the component. We then bring the beam in from the other side, and we detect it on our target, which was the zero-dur instrument I showed in the previous slide. And this gives us a measure of the rotation and position. So we get 5 degrees of freedom measurement of the optic alignment with laser systems here. The only one we're not measuring is the translation one, which, since our optics are planar, we're insensitive to, so that one doesn't matter. So the system is holding the optic 100 microns up, and we're then feeding back these 5 degrees of freedom signals to align the component in the correct place. So we're holding the component in the correct place. We know it's aligned. We can see it. The hexapod then retracts the optic. And then this is the one bit that's still manual in this process, is a person will come in and will deposit about 0.8 microliters of sodium hydroxide, which is the magic that makes the catalysis bonding process happen. And we then bring the optic back down. And then we're holding it back to about 100 microns off. The system will now step it down through 10 micron increments until we make contact with the bonding fluid, and then we spread it out. This is sped up a few times, but what I've just shown you takes about 10 minutes. And that optic is now bonded. You get a 2-minute window where you can decide to abort it, and then it's in place forever and is never coming off. So one of the interesting things about this is that it's new and it's novel, which terrifies engineers. So ESA absolutely insisted that we show them that this thing really works, and that we can do this again and again and again and again and again, and it works. So this is why we made this board with all the fused silica discs on it, so that we could do a campaign to demonstrate bonding lots and lots of optics with this thing. So we bonded 20 optics, all precision aligned at the level that needs to be done for the highest accuracy component in LISA, and these were done at a rate of 2 per day. This represents 2/3 of all the critical alignments that have to be done to do the full set of flight optical benches. You might ask, why did you not just do them all? Well, there are actually 30 bits in this, and we did actually plan to do 30. But for reasons I'll show you in the next slide, ESA just told us to stop. We even tested aborting. So we have an abort process. If this goes wrong, you get this 2-minute window where you have to decide, is this optic correctly aligned? Or what am I going to do? Am I going to commit or am I not? So you have a 2-minute window. And we have a process for aborting in that window. We tested that a couple of times here as well, and then went back and rebonded in the same spot with success. And this is what we managed to achieve. So the red lines are where we need to be. This is the lateral alignment, and this is the angular alignment. And this is not of the optic. This is the alignment of the laser beam to an interface. So this could be the alignment of the laser beam to the test mass, or the alignment of the laser beam to the telescope, or the alignment of the laser beam to an interferometer. Those are the 3 places we need to be. And over the 20 optics, we managed to do lateral alignment about a factor of 3 better than we need to do for LISA. And we managed to do angular alignment at least a factor of 2, probably slightly more than a factor of 2 better. over these 20 components. And either were watching this process and told us at 20 that we could just stop and we didn't have to do the rest. So this has been a major achievement for us. This is one of the key things that went into the adoption process, because this was regarded as a critical technology that had to work in order for the mission to be adopted. So this has been a big achievement, and I will leave it there. Thank you.
Thank you. Thank you. We have time for a few questions for Dr. Fitzsimons. Yeah, we can start in the front and then go in the back.
Thank you. Very nice. So can you just go back one slide?
This one?
Yes.
Yep.
On the angular alignment there, you're well within bands, but most of your measurements seem to be one side of zero. Is there any understanding of why it's
Yeah, it's almost certainly that's the so a big chunk of those error bars I'm showing will be systematics in the coordinate measuring machine, and we were using roughly the same part of the volume of the coordinate measuring machine for all these measurements, and a lot of the systematics in that are due to the bow in the axes of the CMM, and so you'll get the same sort of measurement errors every time. So we think that's a systematic in the CMM.
That's the size you're talking about?
No, the sign as well. We think part of that offset is a systematic in the coordinate measuring machine.
Okay, thanks.
In the back?
Thanks, Melanie, for the talk. I just had a question. The bond strength between surfaces, how sensitive is it to the smoothness of the mate faces?
Vary. These have to be precision polished surfaces, so we spec 1 nanometer RA roughness. You can bond things that are a lot less rough. You can bond different materials as well. There's lots of research in this, particularly from the Glasgow group looking at ground-based gravitational wave detectors. But basically, if you want high strength bonds, they have to be precision polished, very conformal surfaces. So these are surfaces which are flat to few tens of nanometers over the full bond area, and with very low roughness.
There are other questions for the speaker? Yeah, there's one there and one there. So maybe we have time for two more. Yeah.
A quick question. Thank you for the talk, by the way. Very nice. So how far did you test these inserts into titanium and their bonding to the Zerdur plate? Because in ground-based telescope, that is a critical geometry, let's say. It's a choice that gave issues at least ground-based.
The insert or the flat? Or the flat?
The adhesive.
The adhesive.
Yes.
There's currently a massive test program campaign underway to test the adhesive and test the allowables in the adhesive. So many samples of bits of titanium are being bonded to bits of Zero-Dur and will then be cycled and broken, and various other things will happen in order to really make sure that this works. And that will all happen before we glue these flexures onto a very expensive piece of Zero-Dur and put it on a shaker table.
Hi.
Hi, Quinn.
Thanks, a very nice talk. I was wondering what keeps you up at night in terms of instrumental and performance challenges. Is it
that's both a good question and a terrible question. A lot of the things that keep me up at night actually are not so much to do with the OB, but other interferometry stuff. OB related, the one that most terrifies me is luckily also something that's very low probability, and we really have a handle on it. But it's are we really sure that the wavefront error 2.5 million kilometers away is right? And because the lens in the fiber injector is one of the main limiting things. You know, it's this size, and this curved, it's aspheric as well, so it's not even a sphere. So this funky surface is doing the bulk of your work in collimating this laser beam, and that has to be good over 2.5 million kilometers away. But you know, measuring wavefront is a done thing. And we're also, other missions have sent laser beams over distances longer than a LISA arm length now. LISA will not be the longest transmission of a laser beam that is then detected. It was done on, I want to say Bepi Colombo. I think one of the Mercury missions sent a laser back to Earth that was used for comms over a much larger distance. So we will not be the first to do this. And it's not often in LISA we get to say that but on this one, we will not be the first to do this.
Maybe we have time for another very quick question out there. And
hi, thanks for the talk. Once you place the optical component, how do you apply corrections on the tip on the tilt? Because I can imagine that you can rotate, but
you don't. The tip and the tilt this way, you don't. The bond will do it for you. The bond layer ends up being about 100 nanometers thick, so
okay.
it's an extremely conformal process. You basically you've got a reference from the interferometry, so the interferometry system can balance it at about an arc second, and you use that as your reference as you take it down, and you hold it nice and parallel to where it wants to go. But at the end of the day, if you try and correct it, this bonding process has a lot of strength. It will really pull the surfaces together, and if you try and misalign it, it will fix itself, and then you'll be in a situation where, as it fixes itself, it might misalign in the other degree of freedom that you care about. So you let the bond do it.
okay, thanks.
that's all the time we have before we go to the next speaker. You can always catch the speaker in the coffee breaks. So thank you again. Let's thank the speaker. And thank you.